welcome to the weekly PFT colloquium. Today we have a pleasure to hear a talk of Michał Matuszewski, our professor, youngest in the sense of working period in CFT, but also still working with the Polish Academy of Sciences. And Michał has been working on the polaritons, and today we'll hear a talk about confined exciton-polaritons for integrated quantum technologies. So Michał, the ground is yours.
Thank you very much. So I should, yes, I actually forgot to put my second affiliation. So I joined the Center for Theoretical Physics last year, but I'm still partly employed in Institute of Physics for the next year, let's say, to finish my project.
The cursor is blinking, so I can still add it very quickly.
Sorry?
The cursor is blinking, so I can still add it very quickly.
I think it's PDF file, so.
Okay.
Yeah. So, and today I would like to talk about exciton-polaritons and how they can be used for integrated quantum technologies. So this is exciton. I've been working on exciton-polaritons for many years now with collaboration with experimental groups. And on the other hand, there was some discussion recently about the colloquium and the necessity to provide introduction. So I will try to make introduction so that when people who are in the field of astrophysics can hopefully I will succeed, that can be also they can take something from it. Okay, so I will start with introduction to the topic. So what are exciton-polaritons? Well, exciton-polaritons are hybrid particles, so-called quasi-particles, which are strongly coupled matter excitons. Excitons are just electron-hole pairs, which exist in semiconductors. You can think of it as, let's say, a kind of hydrogen atom, where we have electron and the hole. Of course, the difference with the hydrogen atom, that the mass of the hole is much smaller than the mass of the atomic nucleus, but many properties of them are very similar to properties of an atom. And these excitons can be created in a semiconductor just by interaction of this material with light. So if we have a photon, let's say a photon which is usually for exciton-polaritons, we need some confinement of photons. So here what you can see is a photon confined between two Bragg mirrors. Bragg mirrors are very high reflectivity mirrors. And we have a standing photonic wave. Now, photons in this standing wave can be absorbed in a layer of material, semiconductor material. It's a slightly different semiconductor, which where you can say that the conditions for excitations of those excitons, creation of those excitons are favorable. So whenever photon passes through this material, there is some probability that it will excite an exciton, so that the photon will be absorbed and an electron-hole pair will be created. And if the frequency of the photon is matched to the energy of such excitation, such exciton, then under certain conditions of if this, let's say, the rate of this process is higher than the decoherence, we should say about polaritons. So hybrid exciton-photon quasi-particles instead of separately about photons and excitons, because then these exciton-polaritons become eigenstates of the system. You can think of it as a kind of state which is similar to a Schrödinger cat state in some sense. So either you have an exciton or a photon. If you have a polariton, it means that either you have exciton and photon. But this is a coherent superposition, so there is some quantum amplitude of having exciton and some amplitude of having a photon. Of course, if you have many polaritons, you can have excitons and photons at the same time, but this is the basic the basic shape looks like this. So what are the interesting properties of such quasi-particles? Well, one interesting thing is that if you put this, if you like couple these particles in a microcavity, such as depicted here, then you kind of fix the momentum of the photon in this direction because it just corresponds to the momentum of the standing wave. But you have still freedom to have momentum of this polariton in the direction which is parallel to the surface of the mirror. So you can plot the dispersion of particles in function of this parallel momentum. And okay, if you have just photons in free space, we know very well that the dispersion is linear. If we have massive particles like excitons, the dispersion is parabolic. So when you couple these two particles together, you expect some kind of anti-crossing and formation of lower branch and upper branch, which are called polariton branches. But now, if you plot the same dispersion, but in function of this parallel momentum instead of total momentum, you will see that also the lower polariton will have a parabolic dependence of energy on the parallel momentum. So it means that in some sense you are creating an effective mass for both this lower polariton and upper polariton particles. So from massless photons with linear momentum, we are getting massive polarity. So, okay, so the basic, let's say, Hamiltonian that describes this exciton-photon pair looks like this. This is the simplest possible form. So you have some energy of excitons, you have energy of photons, and you have coupling between them given by so-called Rabi splitting. And when you can easily diagonalize this Hamiltonian and find eigenstates of the system by finding eigenstates of such a simple 2x2 matrix. And then you will get such dispersion of lower and upper polarity.
So those excitons are that's bosons here?
Yes, so approximately bosons, because excitons are two fermions. So they form approximate bosons. But this is only an approximation which works at low density. If we go to higher density, so where the excitons, let's say two excitons can come so close together that they feel each other, then actually you can feel this fermionic nature of electron and hole, and this commutation relation becomes more complicated. But for most experimental conditions, you can treat excitons as photons. Okay, so what are other properties of exciton-polaritons? So we have particles which have some photonic part and some excitonic part. And this particle, we have some properties of matter and some properties of light. One property is that the transport is very effective because photons can propagate very quickly, and even if you have massive particles here, this mass is still very, very low. It's much lower than mass of the electron. So the transport is very effective. But on the other hand, you have this matter component, which means that the interactions between polaritons are quite strong, almost as strong as interaction between excitons. So it allows you to somehow introduce strong interactions to photons. You can think of it this way. And this leads to interactions which are actually very, very strong in compared to other non-linear optical materials that you can find. On the other hand, polaritons still have short lifetime because these mirrors, I told you that these are very high reflectivity mirrors, but their reflectivity is very high, but still not perfect. So it means that from time to time, these photons can leak out from the cavity. This is the main sources of losses. And this leads to a lifetime which is on the order of picoseconds usually.
Excuse me, when you talk about transport, you mean in the direction parallel to mirrors?
Yes. So I'm talking about transport in this direction.
So the mass doesn't matter. Because the mass is in the perpendicular.
Mass is actually in this direction. So this plot is function of the momentum in this direction. This part of momentum is fixed. Okay, so another thing, because the polaritons are in good approximation bosons, they can undergo Bose-Einstein condensation. So it means that by pumping particles to high density, we can achieve a transition where most of the particles are actually in the ground state of this parabolic dispersion of lower polarity. This allows to achieve condensation of bosons even at room temperature, which is much higher than, for example, in atomic gas.
Yeah, wait a minute. You already said that bosonic approximation breaks down if you increase the density because the interparticle separation goes smaller. So how do you reconcile this?
So we are here still in the regime of low density. So this breaking down of the bosonicity of excitons is attained at very, very high density, which is called so-called mode transition, where you have so high density that the one exciton is just next to each other, like the distance is comparable to the radius. But this is not, we can have this bosonic condensation at much, much lower density.
Pardon, Michał, and how do you achieve those high densities, like physically, what you have to do?
So physically, you just pump the system with a laser. So you inject photons. Usually, you inject photons with a higher energy than the energy of the polaritons. And then there is a process of thermalization, of relaxation of energy of this particle. So here, what you are basically exciting excitons, which are not coupled to light, because they are not in this energy range where polaritons exist. But then in this solid state, you have phonons, which interact with those excitations. And the energy is gradually going down, goes down to the range where you have this anti-crossing. You will actually need to describe your system in terms of polarities. Eventually will lead to accumulation of particles in the ground state of this dispersion.
Pardon, actually, I meant like what you have to do in order to break the bosonic approximation.
Oh no.
To reach those super high densities.
Okay. So if you want to reach this, okay, so this is like this. At very low density, there is just no condensation. At some density, you reach condensation. And then if you increase your power of pumping laser, let's say 100 times, then you will reach the regime where you have a breakdown of bosonicity. So it's actually also interesting because there are this can be described in sort of like BEC to BCS transition, sort of this regime where you go to the in the high density regime. But actually, in this talk, I will not be concerned about this high density regime practically at all, because this is at this lower density regime is where we can still have very high, strongly nonlinear phenomena, but not so high density that we break down this description. Okay, so this is in 2006. It was maybe not the first observation, but the first observation that was very clear and of Bose-Einstein condensation. So what you can see here is that if you increase the pumping, so increase the density of polaritons, at some point, these polaritons accumulate in the lowest state. So these are actually images in momentum space, not real space, but the effect is the same, as.
But of course, it's a dynamical equilibrium rather than static.
Yes, actually, I forgot to mention that. So actually, even if you accumulate those particles in this ground state of this polaritons, this is still not the ground state of the system, because the ground state of the system is where there are no particles at all. It's just the vacuum. So it means that there is always some emission that happens. You never reach a steady state of, like, let's say, true condensation of particles in the ground state. So this to remain in the condensate, you need to pump the system continuously.
But this would be steady state, not equilibrium, but steady, right?
Yes.
Exactly.
Dynamic.
Yes, dynamic steady state. All right. So now.
How do you measure energy actually? Because you have very nice measurement of occupation of different energy levels. Say.
So this energy is actually the energy of photons that are emitted from the condensate. So this is not really the energy of the system. This is chemical potential, sort of, in the language of
For the condensate.
Yeah. Okay, so now I'm going to after this introduction, I'm going to, let's say, our results. So recently we were interested in the possibility of creating polaritons in perovskite materials. So perovskites is a group of materials which is nowadays is very, let's say, trendy, mostly because it is of its very strong interaction between light and these materials. It can be used, for example, for solar cells, and this is the main, I would say, industrial motivation. But here we are not interested in solar cells, we are interested in some other things. But here what you can see is that we have very many materials where you can actually observe nonlinear effects and use them to construct integrated circuits, waveguides, ring resonators, and many other things that can be used for example, for modulators, for supercontinuum generation, sources of quantum light. So there are very many applications of these nonlinear processes, and if we can integrate them, maybe we can make a practical device. So, and recently these perovskites appear, and they are interesting because of their, as I said, because of the interaction of light with. So what are perovskites? Perovskites are generally a very broad class of materials that has this structure. I don't remember unfortunately how it's called, but basically you have three elements. And they form that such a let's say quadratic structure. You have smaller atoms and bigger atoms, and this bigger atoms and the biggest atoms are kind of trapped in cages made by these smaller atoms. And this structure makes it provides a very high dipole moment, basically. So it means that this material often very strongly interacts with light. And what is interesting is that there are some methods, technological methods that allow to produce the structures such as waveguides, such as couplers, and other structures in two dimensions. That can be used for creating this integrated optical chips, let's say. And I will now summarize the results of from this paper, where the main author is Mateusz Kędziora, who did this experiment. So, but now a little bit before that, a little bit of theory. So, what happens if we go from optical microcavities to waveguides? So, because as you can see, I'm interested here in waveguides, and before that, I was talking about microcavities. So in the case of microcavities, we have, as I said, this fixed wave vector in the direction. And we have the freedom to choose a wave vector in, let's say, parallel direction. And this gives us this nice parabolic dispersion. In the case of waveguides, what we are aiming at is actually the regime of total internal reflection, because it gives us the very good confinement of light. We don't need this high reflectivity mirrors, then just the effect of total internal reflection provides in principle 100% reflectivity. But now the dispersion is no longer parabolic, it is now at high wave vectors, it is approximately linear. There is also something that is quite important is the slide condition. So basically, if your wave vector and energy are in this area, it means that your wave vector in this direction is too high for the light to be emitted outside. So this is important for confinement of light.
Sorry, what does parameter M stands for?
This M?
Yeah.
So this is just a number. It's like quantum number, which tells you how many. If you have the standing wave here, and this is number of antinodes of. Yes. Okay, so now this is example of structures that can be fabricated in Warsaw, actually in Institute of Fizyki next door, in the group of Anna Sherwin. So you can see that these are very nice structures with very high quality. And maybe I will not go into detail into technology to fabricate it, but it has using some templates where we fill the perovskite inside, and then by some process we remove the template, and we are left with structures that we want. Okay, so we're considering a single waveguide of let's say of the size of several micrometers. And what happens if you want to go to some regime of phase transition, for example, like lasing or condensation inside this waveguide? Well, you can say there cannot be condensation because there is no effective mass anymore. So there is no minimum. So maybe let's keep the name lasing to describe this phenomenon. So as I told you, there is this total internal reflection. So I don't expect that any light will come out of this waveguide directly. However, at the edges, this translation symmetry is like this is a defect from the point of view of translation of the structure. So this total internal reflection doesn't work at the edges. So it means that I expect light to come out of the edges. And this is what happens. So this is these are two images of just light coming out from the structure if I increase the intensity. So below the threshold for lasing, I just see some reflection from this is my laser is focused, so I see some reflection from the laser most. But then if I go over some threshold, I see very strong emission from the edges of the waveguide. So it means that there is some light inside, but I can only see it as coming out from these edges. And this is more detailed description of this. So below the threshold, this red and blue is the spectrum of emission from the center and from the edges. So you see that at the edges there is already some teeth, which corresponds to standing wave modes across the waveguide. And when I cross the threshold, there is very strong emission. So you can see there is completely different scale than here, coming only from the edges. And actually, there are a few peaks. So it means that this is example of multimode lasing. And I can plot the energy of of the peaks in function of the wave vector of which corresponds to the wave vector in this direction. And I can see that it is approximately a straight line, but there is some bending, which means that we can see the effect of anti-crossing between lower and upper polarity. And we can also theoretically describe this system. So what you can see is the cross section through this waveguide. So imagine that now in this waveguide we make a cross section in this direction. So this is the view from the top, and now we just make a cross section in this direction. And this is the result of simulations. So you can see there are very, very many peaks of the standing wave, which is photons bouncing between the edges of the sample. And actually, what we see when you observe the far field emission from this system somewhere here, we can see that the dependence of the angle, we see a clear interference pattern, which looks like interference between two sources. And in this image, you can see the explanation of this phenomenon. So you can see that the emission comes only from the edges, whereas the main part of the waveguide is practically not emitting. So we can model this pattern using a simple interference from 2 point-like sources. And and this is agrees very well with such a simple model. Now, if we want,
So I make a question because maybe I missed. So I see experiment, I see theory, and theory doesn't quite match.
Ah, okay. Sorry.
This to me.
Yeah. This I should explain. So in the experiment, we see mostly lasing from a single mode, like it is shown here. So maybe there's very some emission from a single mode, maybe some other mode also has some emission, but we have only, let's say, a few lines. And the reason for this is that these are the modes for which there is the highest gain in the system. So when we have lasing, usually the mode which is the highest gain is selected by the system, and it grows, its emission grows much stronger than other modes. In this very simple theory, we say nothing about the gain. We just try to predict what is the interference from 2 point-like sources. So that's why this effect is not. Well, okay, this is very simplified theory. We can improve it to take into account this effect.
Pardon me, could you remind, please, what was the threshold that you were talking before, the lasing threshold?
Sure.
Yeah. How it is defined?
So, okay, so maybe I don't have a very good figure here, but imagine that you have your pumping laser focused on this spot, and then you gradually increase the intensity of this pumping laser. Below threshold, you will probably see just a linear increase of the reflected light which is coming from the sample. But when you cross some thresholds, the gain in the system overcomes the losses which are in the system, and then the mode which is inside the waveguide can grow exponentially. So it means that at this point you will have instead of very slow linear increase of intensity, you will have like super linear increase of emitted intensity, so that it completely overcomes this emission, this reflection that you saw before. So it's in experiment, there's no doubt about where the threshold is, because it's very, very clear, let's say, in the dependence of emitted intensity on the image. Okay, so what about this? As I said, this is very simplified theory, but it kind of qualitatively explains why we see such patterns. But we can also describe more complicated structures, and to do this, we we solve Maxwell equations correspond to particle structure. So, for example, this structure is just the structure that I showed before here. As you can see, you still can see emission from the edges, but in some particular places, let's say. And to explain this, we find eigenmodes of the structure in theory. And then what we need to do, because if we just find eigenmodes, we will see that actually there's a lot of polariton density inside this wavelet. But to explain the structure, we again need to take into account that there is a finite light cone of emission. So it means that the photons which are propagating inside this wavelet with very high momentum, they will not be emitted because there is no matching mode with high momentum in the, let's say, in the area. So we need to apply some mass in Fourier space that cuts off the modes beyond the less light cone. This is one thing. And another thing that we take into account is that whenever there is some curvature in the waveguide, it also acts like a defect, and it also is a place where the emission can come. So we can reproduce this emission patterns quite well. Okay, so this was the results of the published experiment, and now I would like to say something about the next paper that is more recent. And so, because you can ask what we can use these perovskites for, and our proposition is to use them for optical neural networks.
For what?
For optical neural networks. And a short motivation why we want to have such devices. As you can see, this here is the training cost in US dollars of training different machine learning models. So as you can see, this growth is exponential because the scale is logarithmic. So it means that we need more and more electricity, more and more money to train these models. And
I would
this
argue
is
that it was only exponential until 2018, 19, and then it maybe flattens because there's no more dollars, of course.
I think it will flatten because there's limited amount of electricity that the Earth can provide.
It's easier to produce dollars than electricity.
Yeah.
So then we need to pay for electricity.
Yes. So anyway, so you can see that it's unsustainable. We cannot have such a growth indefinitely. And what is the problem? Because we are used to a situation where there was Moore's law, and we had better and better computers faster, and every 2 years, and there was no problem with electricity. But actually, as electronic circuits get smaller and smaller, we reached the level where so-called Dennard scaling no longer works. So as we decrease the size of transistors, they do not consume less and less energy. So it means that we can decrease the size of transistors, but when you put more of them, you will get more losses. And another problem is that our computers work in so-called von Neumann architecture. So it means that our processing units and memory units are separated in physical space. So, and actually we need a lot of electricity just to send signals from processing units to memory units and back. And this is particularly problematic in neural networks because there we operate with large amounts of data. Okay, so how can we what can we do with it? One proposition is to use photons instead of electrons for computation. This is a very, very old concept. So this concept is older than me. It comes from, I don't know, 60s maybe. But many people tried, but no one succeeded to make it work on a commercial level. So what is the problem? Electrons are very good in information processing, but because they are interacting very strongly compared to photons, but they also are a lossy system. So if we want to transmit information by using current, it generates some losses. On the other hand, photons are excellent for communication of information, but they interact very weakly. So the problem with photons is that they want to make them interact. And the question is whether we can have both at the same time. And it turns out that polaritons is a good candidate for it, because energy needed to perform an operation is, without going into details, is about 4 orders magnitude lower than with other nonlinear materials, just because this is matter strongly coupled to light. And so we propose this concept of using polaritons for creating simple neural networks with my PhD student Andrzej Opala, and then it was realized in several experiments in gallium arsenide and calcium telluride materials. But these experiments were performed at cryogenic temperatures. So now the idea is to use perovskites to to construct polariton neural networks at room temperature, because it turns out that excitons in perovskites are much more stable than in these previous materials, and they can also exist at room temperature. So what we did was we created a very simple neural network with just 4 neurons in a hidden layer. So this is the input layer, hidden layer, and output layer. I will maybe not go into details into neural networks. I guess that many people recognize maybe this kind of structure. So anyway, we have a very simple network with just 4 nonlinear neurons.
I'm sorry, but somewhat familiar with neural networks, but what is very interesting to me is like how you realize like couplings or like interactions between the nodes in different layers. Because yeah.
Okay, so like, this is a very, very long topic. So you can do this optically. So there are very well-known methods to create such vector matrix multiplication by using just, let's say, 2 lenses and a spatial light modulator or some micro lenses. This is because in some way Maxwell equations realize naturally vector matrix multiplication on some level. If you have
okay, so maybe some more basic question. I'm a bit confused. So you shine with lasers on some spots in those perovskites, and those correspond to nodes, right? So what is the degree of freedom that control? Yeah, like that controls value of the node.
Okay, so I should maybe really extend this description. So in the experiments, we did very simplified version of this experiment where what was performed optically was only this hidden layer. So these connections were done on just on a computer. So we just this experiment is very simple. We just have 4 lasers with prescribed power, which is already have the power that corresponds to weighted input from this input nodes.
I see. So power is the value.
Yeah. But so it's not very useful. But what I wanted to say is that there are methods to realize these connections also optically, and then you don't have this necessity to perform all these operations on a computer, in principle.
Sure, but like, do you have to like for every connection? What I mean is it enough to just shine stuff? Like how?
I suggest that maybe we let the speaker finish and postpone it to the discussion afterwards.
Okay. Anyway, so the question is what task you can do with just 4 neurons. So I see that I'm already almost.
No, you have plus 5 minutes because there were quite some questions on the way.
I definitely underestimated the length of my time.
So 20 past, let's say.
Okay, maybe I will finish with this topic.
So you have 10 more minutes, 9 more minutes.
All right. So anyway, we created so a network that can do a task which is recognition of shapes. So this is very simple task, you can say, because just recognition whether we have some square, circle, or a small circle. But the point is that this task is actually very difficult if you just have linear network. If you just have linear network with no nonlinearity, you will never be able to perform this task well. But even if you have just 4 neurons, you can already have very high accuracy of the network. Okay, so now I wanted to go to the quantum regime. What we want to have, we want to have advantage of the fact that instead of processing classical information, we encode information in some quantum state. And the idea is that not only we can kind of perform the same tasks better using quantum computer, which is the principle of quantum supremacy, but we can perform tasks that are not possible to do using classical computers. So, for example, tasks which are based on the input quantum state. So our input is not classical. So let's say that we have some optical input, and we want to say whether these photons are entangled or not. Normally, we cannot just connect the states to a classical computer and hope that it will make it. Usually, what we need to do, we need to do some kind of quantum tomography or some measurement, and then to tell what was the state and whether it was entangled or not, for example. But in this case, what we do, we use a quantum system. So let's say that this is a network of polariton nodes. It can be polaritons or something else, which are quantum nodes on its own. For example, there are 2-level systems. And then what we do, we just measure occupations on these nodes, and then we, for example, decide whether this state was entangled or not, or what were the quantum properties of this state. Yeah, so one example is exactly quantum entanglement detection. Okay, so it was like motivation, and now I won't be able to present this part, unfortunately, because I ran out of time. But I just want to say that because of that, we needed to perform quantization of polaritons in confined structures, which is, as it turns out, it's not well known. It's not basically known how to do this. So we needed to develop some theory. And actually, I had some educational slides about Lagrangian and Hamiltonian because this is something that. So maybe I will just go through the slides, and maybe it will be the other. Because to quantize system, I need to go through Lagrangian and Hamiltonian. So, what is Lagrangian for? Basically, you can describe let's say we have as just a mechanical system, and we want to describe the motion of some massive particles. We can use Newton equations, and that's fine. That is all fine is with that. But we can use another description, which is based on the Lagrangian. And then the point is that, let's say that our motion is restricted. Let's say to this mass can only move on this in this line. So then, instead of solving this equation in calculating what is the force exerted by this constriction to the mass, we can just use so-called generalized coordinates, which is just let's say coordinate of the position of this particle on this line, on this curve, and we don't have to worry about this at all. And we just use Euler-Lagrange equations to determine the motion of the system. And the Lagrangian for mechanical systems, for example, it is just kinetic energy minus potential. For if we want to generalize it to electromagnetic fields, it is also well known. But of course, not always it is easy to find this Lagrangian. For example, I looked because I had discussion with Professor Czerny, and she asked what is the Lagrangian for Navier-Stokes equations. And I could not find a good answer. There are some papers, but they don't. Like it's very complicated problem. And you can generalize Lagrangian to this equative system in many ways, and it is used, but it's also not so simple, I would say. So in some situations, it is easier to use Lagrangian description, and some situations just solve dynamical equation. That's how I see it. And okay, and then there is Hamiltonian description, where we define another function, which is now function of also so-called conjugate momenta, which are defined this way. And then instead of these Euler-Lagrange equations, we have Hamilton equations. And it's another way. It also allows to simplify some problems more. But also what is very important is that it's extremely important in quantum mechanics. So you need to use Hamiltonians to perform canonical quantization, which is, let's say, the way to go from classical to quantum regime. So this is the motivation why we all are so, crazy about Hamiltonians and so on. Yeah, so I think I will finish because
you have 2 more minutes.
Okay, so maybe I'll just so there is some
just advertise the next.
I will just advertise the result that we want to describe on a quantum level a system which is composed of these materials with different refractive index, these excitons and photons. And by the way, maybe not many people know that Hopfield, before he jumped to neural networks, so he received Nobel Prize this year. But before he jumped to neural networks, so he was very interested in polaritons. And actually, the polariton theory is based on his paper from the 50s. But it does not give us the possibility to describe such complicated systems. Yeah, so there's a lot of theory. And in the end, we are able to, using, we find eigenmodes of such confined system, and we can say that the Hamiltonian has such a form just by solving the equations, Maxwell equations. But okay, this maybe it's just. I will not go into details because there's not enough time. So thank you very much for your attention.
Thank you very much, Michał, for the exciting talk. Let me open the question and discussion session. Is there anyone want to ask something?
Just a short comment. There is a well-known phenomenological law which says that energy efficient technologies do not result in overall energy efficiency because more people are using them. And that increases energy consumption. That has been discovered somewhere many years ago. I don't try to currently Google out the name, but this is just the real law, right? Mm-hmm. If you see on the historical development, but that's fine. I have nothing against replacing my Chromebook with quantum computer.
Yes, I think we are now have the most energy efficient technologies ever, but we consume the most energy ever. Yes. So
for cryptocurrency mining, 10% goes for cryptocurrency mining. These are the official data.
Yeah, present price of Bitcoins, it's cheap.
Okay, any more questions? Rajendra.
So, thank you for the great talk. this non-unity is at heart like GKP states also. So is there any work in that direction in the polaritons?
Yeah, so you can ask if we can, for example, reproduce transformer models with optics. So there are some works, recent works, which show how to do this, but they are both based, maybe I would say, on hybrid systems when we have some electronic part, some optical part, and the optical part is mostly used for vector matrix multiplication. So then we don't need so much nonlinearity. So I would say that with these polaritons, if we create neural networks, which are, because the problem is that neural networks that we created are very small. They have maybe 60 neurons. I showed 4 neurons. So you could say that they are useless because an electronics can have billions of nodes, and then we can do ChatGPT. But in fact, there are tasks which do not require so many parameters and so many nodes, and are still very useful, especially if we have a system which is very energy efficient. So, for example, imagine that we have a drone which is flying over some fields, and it has to detect whether there is some disease in this field. But this is something that is maybe you can detect it by image recognition, some spectrum recognition, but you need to process a lot of data. So we cannot just put a very high, very big computer on the board of the drone and fly over it and do it in real time. On the other hand, if you just collect the data, amount of data will be too high to store it and bring it back for analysis. Or if, for example, if you are driving a car, you need to process images which are, let's say, in real time, which have 25 frames per second. And let's say that you want to consider details which are on the order of pixels when you have image which is 1000 by 1000. And you can estimate that you cannot do it using current electronic technology because the amount of data is just too big. If you have optical processing, you can do it faster and more energy efficient way.
An obvious application is, of course, intelligent astronomy, real-time astronomy. There was the dream of Paczynski to have a wide field telescopes, quote unquote, monitoring continuously. And the problem was that still they had to be connected to computer to process data. So I spent some period of my life trying to invent intelligent CCD camera, which would be not only capable of collecting images of the sky, but analyzing them in flight, and we failed. Well, probably such a technology could make a breakthrough.
But it exists in CERN. It's called VITO technology. You don't need to store all the data. You need to be smart with the VITO, because not every physics is interesting. So it can be done, and it's done with LSST now with Rubin. Although you will lose some information, you need to pay the price. Maybe with photonics in future you can have more information and less VITO in this direction.
I would also have a follow-up question. You mentioned the speed. I wanted to ask you, so this handwriting recognition, how fast it is?
Okay, so
from, like, honestly, from input to output, and maybe also how much energy it takes, like compared to a solid state, probably a very basic chip that would do that. Okay, if you have the numbers.
Yes, so these are just proof of principle systems, so they are not very efficient. For example, if we have this digit, they are encoded with spatial light modulator, which has response time on the order of milliseconds. So it will not be faster than what if you use your computer. So we don't believe that this technology can be. I mean, this idea can be used, but you need to replace some elements. Because, for example, there are known optical elements which can do it in gigabits. So it's the matter of improving the components of the system to make it work really efficiently.
But you think that it can be made, that it can beat the solid state chip, doing the same easy task, let's say, recognizing handwritten digits from 0 to 9?
Yes, I mean, if you look at it depends how you ask the question. I don't think that handwritten digit recognition is something that I would say it needs to improve the speed of or energy efficiency.
Because trying to see where it's better. Yes.
So, but we need to think it this way. We need to not only to make a good system, but we also need to find a good application for this system. This needs to go hand in hand. So that's why I was telling about maybe some detecting of like some maybe objects or some events. In my opinion, is much more correlated with the nature of the system, which is very fast and processes a lot of information, but maybe processes it in a very simple way as compared to electronics. So we will not make a better general image recognition or ChatGPT or I don't know, something like this, but we can find some special application where it can be much better than, and then it can be better actually by orders of magnitude.
Okay, got it. Thank you. Tekun, do we have questions from the chat?
No.
No?
Here, we speak that.
I just want to add to what you said recently. 25 years ago, Adi Shamir proposed Twinkle. Twinkle was an optical machine with a lot of LED diodes to factorize 512-bit RSA key. They estimate the cost of machines then would be $5,000, which means nothing compared to electronic computers. Not much has been published after that about those machines. It seems that they are probably working full time. But you can just find Twinkle on Wikipedia or elsewhere, and there is a description. It was very, very smart idea because he observed that if we look at the well and it's dark, we see when it's dark. So it's enough to have one LED with light which came through, then we know which LED it is. And that was this part of necessary to recognize this factorization.
Okay. We have 1 more minute for last short question. And one, please.
Maybe very short comment to make a loop to the astronomy with what you will be discussing. Well, of course, we know Lagrangian as well in cosmology, but the problem is that if the system is not perfectly conserved, you can throw your Lagrangian off because of the regime that is not conserved. But going back to the light, I think among many applications with light computing, astronomers also are one of the first ones. So to my knowledge, first ever n-body simulation for actually that was studying the formation of the bar in the spiral galaxy was done in 1941 by Erich Holmberg when he used light bulbs on a bench to simulate particles because there was no computers, and he just added flags because he exploited the idea that the light intensity drops like a gravity with the inverse of the square of the distance. And actually it was meticulous because he had to calculate the acceleration, but then he had the flags, so there was gravity. So I think the light has a bright future also.
That's a very good finish, I guess. So let's thank Michał again. Thank you very much.